Hello guys, let's talk about the rate law. So this is a mathematical expression that is going to describe the relationship between the rate of the reaction and the concentration for all reactants. If we have a general equation where A and B are the reactants forming some kind of product, the rate law is going to have the following form, where the rate equals to K, which is the rate constant, a temperature-dependent quantity, multiplied by the concentration of the reactants A and B on the exponents M and N. And these exponents are the so-called reaction orders with respect to each of the reactants. Typically positive integers, but they can also be fractions, negative values, or even zero. The overall reaction order is going to be the sum of orders for each reactant. So in this case, M plus N. And in order to figure out the rate law for any reaction, I must do experiments. So notice that here we have the decomposition reaction of dinitrogen pentoxide, and the rate law has the following form, where the rate equals to K multiplied by the concentration of N2O5 on the first order. So notice that the stoichiometric coefficient in the reaction does not agree with the reaction order. It may be the same, but most often it is not going to be. So we need to do experiments to figure out the rate law for any reaction. How do we do that? Let me show this to you using an example. So here we need to use the data in this nice table for this general reaction, and we will have to figure out, first of all, the rate law for the reaction. So notice that in this table, I have 3 experiments. In these experiments, I kept, in some cases, some of the concentrations constant, and some others I changed. So for example, in experiment 1 and 2, the concentration of reactant A is kept constant, but the concentration of reactant B is changed. And I also measured the initial rates. So based on changing the concentration of the reactant and measuring the initial rate, I can figure out the order of the reaction in reactant B. Now I can do the same for reactant A using experiments 1 and 3, because in those cases my reactant B concentration is the same, but I changed the concentration of reactant A. Okay, so how do I do that? I'm going to assume that the rate law for this general reaction has this general form, and I'm going to use proportions to figure out the reaction orders. So I'm going to take the rate of reaction 3, so rate 3, and divide that by the rate of reaction 1. So notice that these are the 2 experiments where I change the concentration of A. So I'm trying to figure out what is the order of the reaction for the reactant A while keeping the reactant B at a constant concentration. Okay, so rate 3, if we look at this general equation, should equal to K, which is the rate constant, multiplied by concentration of A in experiment 3 on the exponent M, and also multiplied by the concentration of B in experiment 3 on the exponent of N. And then I divide that by the rate expression for the first experiment, where it's also going to equal to K. Notice that this is a constant, so K is not going to change as we are not changing the temperatures during these reactions, multiplied by the concentration of A in experiment 1 on the exponent M, and also multiplied by the concentration of B in experiment 1 on the exponent of N. Let's plug in the values and let's see what we get. So rate 3 is actually 2.0 times 10 to the negative third molarity per second, and rate 1 is actually the same value, 2.0 times 10 to the negative third molarity per second. And this going to equal, in both cases, to K, which is the rate constant, multiplied by the concentration of A in the third experiment. So 1.00 molarity on the exponent of M multiplied by 0.50 molarity on the exponent of N divided by 0.50, right? That's the concentration of A in experiment 1. So I need to put it on the exponent M, and then multiply that by the concentration of B in experiment 1 again on the exponent of N. Now, because I have this fraction and in the numerator and the denominator I have the same values, I can actually cancel them out. So I can cancel out the K, and I can cancel out the concentration of B on the exponent of M in both cases. So from here, if I solve this, I'm going to get 2.0 times 10 to the negative third divided by 2.0 times 10 to the negative third. So this part right here is going to equal to 1, and that equals to 1 divided by 0.5 on the exponent of N, right? So that is going to be 2 on the exponent of M. Now, this expression can be true only if M equals to 0. So now I figured out that in this reaction, the order in reactant of A is going to be 0. I hope this makes sense. Let's do the same thing for reactant B. So for reactant B, I need to use the experiments where the reactant A concentration was kept constant. So I'm going to use experiment 1 and experiment 2. See that these values are constant and the concentration of B was changed. So again, I'm going to use a proportion where I'm going to have rate 2 divided by rate 1. So it doesn't matter whether you divide rate 2 by rate 1 or rate 1 by rate 2. It's just generally easier to take the rate expression for the reaction where you have a higher concentration, just generally allows for easier calculations, okay? But there is no other reason for that. All right, so rate 2 is going to equal to K, and we are using the same general expression, multiplied by the concentration of A in the second experiment on the exponent of M, multiplied by the concentration of B in the second experiment on the exponent of N. And this whole thing is divided by the rate expression for the first experiment, which equals to K multiplied by the concentration of A in the first experiment on the exponent of M, and multiplied by the B1, so the concentration in the first experiment on the exponent of N. Okay, let's plug in the values and let's see what we get. So rate 2 is right here, 8.0 times 10 to the negative third molarity per second divided by 2.0 times 10 to the negative third molarity per second, which equals to K multiplied by A2, which is 0.50 molarity on the exponent of M, and multiplied by 1.00 on the exponent of N. This whole thing is divided by K times 0.50 molarity, and don't forget the units everywhere, on the exponent of m, right? This is this value right here from the first reaction, multiplied by, again, 0.50 molarity on the exponent of n, which is the concentration of B from the first experiment. Now, again, I can cancel out the same values in the numerator and the denominator. So the K's will cancel out and the concentration of A will cancel out. And now I can do the calculation. So 8.0 times 10 to the negative third divided by 2.0 times 10 to the negative third is going to give me 4. And 4 is going to equal to 1 divided by 0.5, which is 2 on the exponent of n. So the only way this equation can be solved if my exponent n actually equals to 2. So this means that the order of B in this reaction is going to be second, okay? So second order in reactant B. Now I can write out the overall rate law from here. So the rate equals to K multiplied by the concentration of A on the exponent, if we go back to the previous slide, 0, right? And that is multiplied by the concentration of B on the exponent of 2. So this is going to be a second order reaction. And because anything on the exponent of 0 equals to 1, I can also say that this equals to K times the concentration of B on the second order. Okay, so I hope this makes sense. Now, since we figured out the rate law for this reaction, right? This is the rate expression. Now we can move forward and actually calculate the rate constant K. So let's do it here. So we said that the rate equals to K multiplied by B on the exponent of 2. I can solve for K from here. So K equals to the rate divided by B on the exponent of 2, or more precisely, concentration of B on the exponent of 2. So we can choose whichever experiment we want and then just simply plug in the value. So let's choose experiment number 1. My rate is 2.0 times 10 to the negative third molarity per second divided by 0.50, right, the concentration in B, molarity squared. And if you do this calculation, you are actually going to get 8.0 times 10 to the negative third 1 over molarity times second, or molarity on -1, second on the minus first. Okay, so I hope this makes sense. Now we can figure out the rate of the reaction when we are given different amounts of A and B, or different concentrations of A and B. So let's just do that. In this case, we have to figure out the rate when A equals to 0.1 mole per liters and B equals to 0.3 mole per liters. So we know that our rate expression is K times the concentration of B on the second. And we also calculated K to be 8.0 times 10 to the negative third molarity on the first minus first times second on the minus first. And now I need to multiply that by the concentration of B. So here it is 0.30 molarity on the second, right? Don't forget about the exponent. So now if you do this calculation, you are actually going to get 7.2 times 10 to the negative fourth molarity per second as the rate of the reaction when these are the initial concentrations. All right, I hope this makes sense. See you in the next video.